Hello, hello. So now we have section 4.5. So if you look, there are like 17 examples I pulled from the book, and I skipped the word problems at the end. There's a lot of different ways that these questions can be asked. The first ones are very short, and then they start getting more and more peculiar. We're actually going to see some full-blown quadratics. So I'm going to try to keep it 2 to 3 examples to a video. So there's going to be a lot more here, but this is a very dense section. You don't have to watch them all. Just like scroll in the list till you see one that looks similar to what you're working on and kind of guesstimate which video it'll be. All right. So our first one's here. We have cosine of theta equals 1/2 and sine of t equals 1/2. Now, first thing to notice here is the verbiage. I know you guys love to skip reading. It says all possible. So this is not just look on the unit circle and there's your answers. We're still going to do that, but we also have to do this. So every 2 pi units, so every coterminal angle with an angle that works is also a possible exact solution. Now, obviously, we can't write a list of infinite numbers, but we are going to use this shorthand. So k is a placeholder for an integer because we use I for something else, so k. So what it is we figure out where on the unit circle an equation is true, and then we're going to write plus 2k pi or 2, I actually usually write 2 pi k. I don't know why it says 2k pi. That's actually kind of tripping me a bit. I don't know why they put the plus or minus because k is an integer, so that includes the negatives. And I don't think WebWork will let you type plus or minus, but I don't think WebWork actually asked for any of the k formulas. There are a few equations, though, where if you don't remember to do the k thing, you'll miss some of the answers. Okay. So right here, let's just see how it works. How do we do the 2k thing? 2 pi k. So cosine of theta equals 1/2. So, like, where's cosine 1/2? 1/2 is the short side in a 30, 60, 90. Short side is next to the bigger angle. So this is 60 degrees, which is pi over 3. So that is our first answer. Theta could be pi over 3. Now this is where our all students take calculus comes in. Filled out the same way you go around the unit circle. So this is positive 1/2. Where else is cosine positive 1/2? Cosine's positive in quadrant 4. So I want to know what's the quadrant 4 angle that's also over 3. So pi over 3, here, let me kind of sketch these in. So this is pi over 3, 2 pi over 3. 3 pi over 3 is pi itself. 4 pi over 3, 5 pi over 3. So our other angle is 5 pi over 3. Now on to both of these. I'm going to write plus 2 pi k plus 2 pi k. So, and then technically we're all supposed to write where k is an integer. All right, so pi over 3 up here, and every coterminal angle, including if we go backwards, and 5 pi over 3, and every coterminal angle with that. There is not a way typically to combine these. Every rare once in a while, they like perfectly line up and you can, but it's usually you just leave it as 2 separate equations. Like, so don't try to be like, how could I write this as? Don't try to write it as 1, it's 2. Now, WebWork doesn't have a good way for you to type this in. So all WebWork would be looking for is instead of all possible, they'll say, find all the solutions between 0 and 2 pi. And if they say 0 and 2 pi, that means you better type your answers in radians, not degrees. So here, they didn't actually tell us, but the 2 pi thing is a radian thing, we typically answer in radians, just because it's a unitless measure. All right, so same song, second verse, but now sine is 1/2. So that's the short side, but it's the vertical short side. So that is, see, that's where sine would be 1/2. That's our smallest angle. So this is 30 degrees, which is pi over 6. And t could also be all students. Sine is positive over here. So I need another little part of the bow tie. So see, all the angles that share the same size of sine, whether it's positive or negative 1/2, form this little bow tie shape. So 30 is pi over 6. 2 pi over 6, 2 6 reduces, 3 6 reduces, 4 6 reduces, 5 6 does not reduce. 6 over 6 does, 7 over 6 does not. So it's all the ones that don't reduce are the ones that we get 6. So 8, 9, 10 all share factors with 6. 11. And then 12 pi over 6 would be 2 pi, which is back where we started. So we want to use this one and this one because it's positive. So we have pi over 6 and we have 5 pi over 6. And then we're just going to go throw back in the plus 2 pi k plus 2 pi k. So that is all the possible places where sine of that number would equal to 1/2. That's a lot. But that's how we do it. We found the 2 initial values on the unit circle and then wrote the 2 plus 2 pi k for all the coterminal. All right, one more. So 3 here, like, it looks a little weird at first, like, oh, I don't know, Liz, that looks freaky. So first, kind of distance yourself from the cosine theta in there and just think of it as ugly. In fact, I'm just going to write u for ugly in place of it. So this is 2 uglies minus 3 equals -5. I'm trying to solve for ugly, so I'm going to add the 3. So I have 2 uglies is -2. And then to get ugly, this is 2 times ugly, so divide by 2, divide by 2. So our ugly is equal to -1. And now I'm just going to undo my ugly. What was ugly again? Oh yeah, cosine theta. So this is really asking, when does cosine theta equal -1? Well, if I think about my graph, because that's what I do for any of my ones and zeros, it starts at +1, and then 2 points later it's at -1, that is pi. Or on the unit circle, -1 is to the left, which is pi radians. So we have theta equals pi, technically plus 2 pi k, but I take a gander back up here and this one said, oh, no. Only the stuff between 0 and 2 pi, but not 2 pi, because that's 0. So the only one that's actually in that range is the initial number we got itself, pi. So that is our singular answer to this particular equation. So even when it looks a little ugly, like still, if there's only one trig guy, it will eventually look just like example 1 and 2. You just might have to do a little algebraic manipulation. This is why I said it's going to use all your skills together. All right, so let's cut this one so we can start the next one.